Hi there, Miss Barber here. Today we're going to learn the skill of integration by parts. Integration by substitution is the reverse of the chain rule for differentiation. Similarly, integration by parts is a reverse of the product rule for differentiation. We have one learning objective for this lesson. It is to be able to integrate by parts. So integration by parts. For differentiable functions u and v, the product rule states, so let's recall, the derivative with respect to x of the product u of x times v of x is equal to the derivative of the first, so u prime of x times the second v of x plus the first function u of x times the derivative of the second, or v prime of x. Now, let's integrate all three parts. That would give us the integral of d dx of u of x times v of x, and that would be equal to the integral of u prime of x, v of x dx, plus the integral of u of x times v prime of x dx. So let's complete the integral. The integral of the derivative just gives us the function. So it'll be u of x times v of x, and we still have the remaining two parts, the integral of u prime of x, v of x dx, plus the integral of u of x times v prime of x dx. To simplify this, let's write this again, but we'll drop the of x part. So we'll end up getting u times v is equal to the integral of v, that's the function, and u prime of x dx is just du, the derivative with respect to u. Similarly, for the second part, we'll get plus u times, and then v prime of x dx would just be dv. Let's solve for the integral of u dv. That would give us u dv is equal to uv, and then we subtract the integral of v times du. This gives us the setup for our next theorem. Theorem, integration by parts formula. For u and v differentiable functions, the integration by parts formula gives us the integral of u dv is equal to uv minus the integral of v du. Let's make a few observations. The integration by parts formula does not tell us how to integrate anything. In fact, when confronted with a difficult integral, say the integral of u dv, this formula allows us to exchange it for hopefully an easier integral v du to integrate. Thus, being able to identify the correct u and v is essential. Some thoughts and hints for using integration by parts. Every component of the integrand must be part of u or part of dv. Leave nothing out. That is, match the integral of f of x times g of x dx to the integral of u dv. Keep in mind that dx is always a part of dv. Find du by differentiating what you chose for u. Find v by integrating what you chose for dv. How to choose the u? A simple rule, LAE, logarithm first, algebra next, and exponential function last. Example, integrate x e to the x dx. By process of elimination, we know that this cannot be integrated directly, and it cannot be integrated by a method of substitution, so we're going to do so by integration by parts. We need to identify the u and dv of the given integral. The LAE rule says we pick the exponential function as the last possible choice for u, so we'll let the exponential function e to the x dx be the dv. Then by default, the term that's remaining is x. To find du, we take the derivative of u. So the derivative of u gives us du. The derivative of x gives us dx. To find v, we integrate dv. And the integral of e to the x dx is one of our rules, and it's just e to the x. The integration by parts formula is that the integral of u dv can be solved as u times v minus the integral of v du. Now we're going to replace all the u's and dv's and du's and dv's in terms of x. So we'll write this again. U is x, dv is e to the x dx. This is the integral we're trying to solve. And that's equal to u, which we identified as x, and v, which we identified as e to the x. Then we do minus the integral of v, which we identified as e to the x, and du in terms of x is dx. Now we can integrate the remaining part, so the x e to the x stays put, and the integral of e to the x is just e to the x, and don't forget the c. So now we solved that the integral of x e to the x dx is x e to the x minus e to the x plus c. Example, integrate ln of x dx. What we do know is that while we can integrate 1 over x to get ln of x, we don't have a direct integral for ln of x. Furthermore, there's no substitution here, so by default, we now need to do integration by parts. To do integration by parts, we need to identify the u and the dv. Our rule tells us L, A, E. L is the first choice for u, and in this instance, the L is the log, so we'll let u be the natural log of x. Then by default, the only thing remaining for dv to take on is dx. To find du, we find the derivative of what we set equal to u. And so the derivative of the ln of x is 1 over x dx. Now, to find v, we integrate what we set equal to dv, and so that's actually a constant of 1, so the integral of dx gives us x. Now let's set up the integration by parts formula, which is that the integral of u dv can be computed as u times v minus the integral of v du. Let's replace the stuff that's in u's and v's with the x corresponding terms. So the integral of u dv, u we put back in ln of x, and for dv we put back in dx. For u, we'll put back in ln of x. For v, we put in x, minus the integral of, for v, we put in x, and for du, we'll write 1 over x dx. We'll further simplify and write this as x ln of x minus, and then the integral of x times 1 over x is just 1 dx. We'll continue. The x ln of x stays put, minus the integral of 1 is just x, and don't forget the plus c. So we have that the integral of ln x dx is equal to x ln of x minus x plus c. Example, integrate negative 8x ln of x dx. For this problem, I'm going to switch the order of the terms, and I'm going to write this as the integral of ln of x first, and then times negative 8x dx. Now we'll begin the integration by parts process. We need to identify the u and dv The LAE tells us if you have a log, use that as your first option for the u substitution portion. So we'll let u equal ln of x. Then by default, the remaining part is negative 8x dx. To find du, we take the derivative of what we set u equal to. So the derivative of the natural log of x is 1 over x dx. And to find v, we integrate what we set dv equal to. So we need to integrate negative 8x dx. And if you do that, you could do it on the side. You can do negative 8x dx. That would be negative 8, and then you're going to have 1/2 x squared plus c. And so negative 8 times 1/2 will give us negative 4x squared. Now let's take the integration by parts formula. That's the integral of u dv, and that's equal to u times v. And then we need to subtract the integral v du. Let's replace the u's, v's, dv's, du's in terms of x. So we're going to have the integral of u, which is ln of x, and dv we identified as minus 8x dx. And that's equal to the product of u, which we identified as the ln of x, times v, which we solved to get minus 4x squared. Then we'll have minus the integral of v, which is negative 4x squared, and du, which we got as 1 over x dx. Let's write this again. I'm going to revert the integral back to the original presentation. So I'm going to integrate negative 8x ln of x dx is equal to, I'll write the polynomial term first, so negative 4x squared ln of x. Now let's be careful with the algebra. The negative and negative gives us a plus. The 4 is a constant, so we could take it to the left of the integral symbol. An x squared in the numerator and an x in the denominator gives you 1x dx. So let's integrate that term. Then you have negative 4x squared ln of x, nothing changed, plus 4. And the integral of x, remember you add the power, so you're going to have x squared, and divide by that same power. Don't forget the plus c. So when solved, the integral of negative 8x ln of x dx, that's equal to negative 4x squared ln of x plus 4 times 1/2 would be 2x squared, and don't forget the constant plus c. Example, integrate 5x squared times e to the 2x dx. Before we actually do this integration problem, we're going to do 2 pre-integration problems. I'd like to start by first looking at the integral of e to the 2x dx. This integration problem will be solved by method of substitution. So let's do a quick reminder. Method of substitution. Substitution. To do so, I'm going to let u equal 2x. Then du is the derivative of 2x, which would give us 2 dx. The issue is, in the original problem, we have a dx, but not 2 dx. Well, divide by 2 on both sides. That'll give you 1/2 du equals dx. Now let's make that substitution. So we want to integrate e to the u, where the 2x was, and where dx was, we'll replace it with 1/2 du. Let's put the 1/2 on the outside of the integral symbol. So that is equal to 1/2 the integral of e to the u du. In integrating, we'll get 1/2. The integral of e to the u is just e to the u. Don't forget the plus c, but we need the answers in terms of x. We'll substitute back. So you got 1/2 e, and where u was, we put 2x plus c. So let's mark that the integral of e to the 2x dx is 1/2 e to the 2x plus c. That's pre-problem 1. Again, before we get to the actual problem, I would like for us to integrate x e to the 2x dx. This is an integration by parts problem as well as our example problem, but a little bit more straightforward. And we're familiar with how to do this. You got to find the u and dv. So we're going to choose u to be the x because the LAE rule says choose exponential as your u as a last resort. So the dv would be 2 to the x dx. To find du, you have to take the derivative of what you set u equal to, and so the derivative of u is du, the derivative of x is dx. Now, to find v, you have to integrate whatever we set dv equal to. We set dv equal to e to the 2x dx, and we actually found that integral in the previous problem, and so we know that the integral of e to the 2x dx is 1/2 e to the 2x. Let's solve. The integral of u dv is equal to the integral of u times v minus the integral of v du. So our integral x e to the 2x dx is equal to, where u was, we'll put in x, where v was, we'll put in 1/2 e to the 2x, and then minus the integral of v, which is 1/2 e to the 2x, and du is dx. Continuing, we could write this, put in the constant first, so 1/2 x e to the 2x. Then we need to integrate. Let's put that 1/2 outside the integral symbol. So the integral of e to the 2x dx. Guess what? We've already integrated e to the 2x dx, so now we'll have 1/2 x e to the 2x minus 1/2, and where e to the 2x dx was, we'll put the integral in, which was 1/2 e to the 2x, don't forget the plus c, and so when we simplify this, that will give that the integral of x e to the 2x dx is equal to 1/2 times x e to the 2x minus the 1/2 times 1/2 is 1/4 e to the 2x plus c. Now we are ready to integrate the 5x squared e to the 2x dx. For that integral, we need to identify the u and the dv. So we know that for the dv, we want e to the 2x dx. Then by default, what remains for the u is 5x squared. To find du, we take the derivative of u. The derivative of 5x squared would be 10x, and don't forget the dx. To find v, we integrate dv, and that was the very first pre-problem we did, and that gave us 1/2 e to the 2x. Now let's set up the integration by parts formula. That is the integral
of u dv is equal to u times v minus the integral of v du. Let's put in everything in terms of x. So we'll have the integral of u, which is 5x squared. dv is e to the 2x dx. That would be equal to u, which we identified as 5x squared, and v, which we solved for as 1/2 e to the 2x. Now we need to subtract the integral of v, which would be 1/2 e to the 2x, and du, which we saw for as 10x dx. Let's do some algebra as we continue. Multiplying the 5 and 1/2, we'll have 5/2, and then we've got x squared e to the 2x. Now let's look at the terms within the integral. You have 1/2 and 10. Multiplying those together, it's a 5, and we can move it to the left of the integral symbol, and we still have x e to the 2x dx. Let's note the integral of x e to the 2x dx we solved previously, and so now we'll replace that integral notation with the actual integral, and our answer will be 5/2 x squared e to the 2x minus 5 times the integral we previously obtained, which is 1/2 x e to the 2x minus 1/4 e to the 2x plus c. Then we have one final step to do, and that is to distribute the -5. So let's do that. And when we do, we solve for the integral 5x squared e to the 2x dx is equal to 5/2 x squared e to the 2x minus, now distributing that 5/2 x e to the 2x minus 5/4 e to the 2x, and plus c, any arbitrary constant.